All right, welcome back to another calculus lecture. Today we introduce officially the concept of a derivative, although in the last lecture we sort of already saw this fairly well. I just didn't call it the derivative, but really it was the derivative, and that's what we saw there. But let's recall what we did last time. So last time we defined instantaneous velocity maybe at the point A, at the point, or maybe, t equals A, as, we gave a limit definition for it. It was the limit as h approaches 0 of s of a plus h minus s of a divided by h, where s of a was our position function and h is this width of the time interval around the point A. Okay, and remember the idea was that if I wanted to compute an instantaneous velocity, what I should look at is actually the limit of average velocities, which is precisely what this quotient represents. It's a change in position divided by a change in time. I look at the average velocity as the time interval shrinks to 0, or the width of the time interval shrinks to 0. So this is a very specific example where my function depends on time and the output is a position. Well, more generally, we can define and instead of an instantaneous velocity, really what we have is an instantaneous rate of change define the instantaneous rate of change of a function f of x. So any function, just depending on some variable x, at the point x equals a. There's no reason why we can't just take this definition that we used for instantaneous velocity and just apply it to a more general setting of an abstract function which is going to have a rate of change. Maybe it doesn't depend on time and maybe our output isn't position, but the notion is still the same. And so that brings us to our definition of the derivative. So definition, and this I will preemptively mark with a red star because this is a very important definition. Important to understand this and really know what the notation is saying. So the derivative of a function f of x at the point x equals a is the instantaneous rate of change at that point okay, and is given by the following limit. And we're going to define the notation f prime of a to just be this limit. So if I write f with a prime on it, I mean literally insert this limit. So limit as h goes to 0 of f of a plus h minus f of a divided by h. Okay, And this is what we will take as our definition of the derivative, at least at a particular point A. And if, one more thing to say, this limits don't necessarily have to exist. We've seen examples already. When we go to compute a limit, the limit for whatever reason, due to discontinuity, due to this, that, and the other, does not exist. And so, if this limit exists, because it need not always exist, but if it does, then f is said to be differentiable at the point x equals a. So if I go to compute this limit of some generic function that I'm putting in here, if I compute this limit at a fixed value a, maybe a is 2 or 3 or the square root of 17 or whatever number you want, if I go to compute this limit and it exists, then the derivative exists, and we say that the function is differentiable at that particular point. Okay, so this gives us a way to compute derivatives at particular points. In the last lecture, we did some examples of computing limits like this, so I won't go through that again immediately. I want to do something else first. And the thing that I want to say is that, well, this is at a particular point, but there's no reason I can't just define the derivative as a function where the f prime of x maybe instead of a here, so now x is just going to be a generic variable. If I just swap out a with x everywhere, then I can define a new function as this limit. So continuing on, maybe, how do we want to say this? The function f prime of x is defined to be the thing that you get when you compute this limit. But now I'm not going to have a fixed value of a. So now the expression right here, x is not a number. X is a variable, and so if you want to compute this limit, you have to be a little bit more careful. You can't just put in numbers and then compute everything. You actually have to treat x as a generic variable and compute the limit. And then finally, I'm getting to the bottom of the page here. Yeah, there we go. The function f prime of x is called the derivative of f of x, presupposing that this limit exists at all the values of x that we're interested in. We've defined differentiability at a point, and so you can extend this to say that a function f is differentiable if it's differentiable at all of the points in its domain. We're not going to hamp on that point too much, but really what's important is this limit definition for the derivative. So I'll use a straight edge just to make this look even nicer when we look back at this later. This is a very important definition. This is really what makes a lot of calculus go round, at least the first half of the course that we're going to be focusing on for a while. So this is the derivative of a function, and just as in the same way as we defined instantaneous velocity, this represents the instantaneous rate of change of the function. And so if I want to compute that rate of change at a particular point, all I do is use this limit. Or if I want to have an expression for the function and then an expression for the derivative so that I can compute the derivative easily at any point rather than having to go through this limit process every time, I can compute this limit for a general x and then obtain a function. So let's do some particular examples of computing derivatives. So first example, and this kind of harkens back to what we did yesterday. So let's let f of x equal x squared, and we want to compute f prime of x. Okay, and maybe we'll say using the limit definition. Okay, so I want to compute this limit, and I can do that by just inserting the limit definition. So let's just write that down. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. So this is just copying verbatim what the limit definition is. If I ever tell you to compute a function using the limit definition, this should always be your first step, is to just write down what the definition says that the derivative is equal to. And then the next step is let's just insert what our function is. So what is our function doing? Well, it's taking our input, x, and then just squaring it. It's taking that number and multiplying it by itself. So if we put that in here, then we get x plus h squared minus x squared divided by h. And now we could be clever. I kind of remarked on this last time that we could try and factor a difference of squares or do something like this. But I think it's easier to just expand this square and compute the limit that way. So this is going to be equal to the limit as h goes to 0 of, well, what do we get when we square this out? X squared plus 2x times h plus h squared, and then minus x squared, all divided by h. And now what do we notice is that the terms that involve x squared both cancel out with one another. I have an x squared minus x squared, so I get the limit as h goes to 0 of 2x times h plus h squared divided by h. And this is very good because before I had like a 0 over 0 coming out of my limit, but now if I go to compute this, I get to divide the h's through on this quotient right here, because h is never equal to 0 in the limiting process. So this is equal to the limit as h approaches 0 of 2x plus h, and then this is now a continuous function of h, so we can simply evaluate it and say this is 2x. And there we go. We've computed the derivative of x squared using the limit definition. And if you recall last time, I had you, we computed the instantaneous velocity at a particular point, and if you go back and look at the notes, you'll notice that the derivative is twice the value at that particular point. Okay, so that's an example of how we can use the limit definition. Let's maybe talk about what does this look like graphically. So the derivative graphically. Got to make sure to age restrict this video because we're getting very graphic here. Okay, so let's go ahead and get a nice little coordinate axes here, and we're going to use this function as our example. So if I let's see, where do I want to go here? Yeah, we'll go down one more. So if my coordinate axis is this, And I'm going to mess up at the centering on it. Ah, well. That's not too bad. And then let's see, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. If I was a better lecturer, I would have had one of these already drawn out. Oh well. So let's go ahead and graph f of x equals x squared. So maybe we'll use a different color because I like to keep my lectures lively. So if I just plug in some points, so at, I guess I should label my axes, by the way, 1, -1, 1, and -1, so all of these have the same scale. If I draw x squared, then at 1, 1 squared is 1, -1 squared is 1, 2 squared is 4, -2 squared is also 4, and the graph's going to look roughly like this. A little bit too sharp down here, but you get the point. So this is f of x equals x squared. And now I want to draw the derivative of x squared. So the derivative is 2x. So at 1, I'm at the point 2. At 2, I'm at the point 4. At -1, I'm at the point -2. And at -2, I'm at the point -4. And so if I draw this is really just a line. Then my derivative looks something like this. And the main thing that I want to point out right now, there's a lot we could say about what the derivative represents graphically, but the main observation that I want to note, so observation, is that what happens if the derivative is negative? So the derivative being negative just means that this pink line is below the x-axis, so we're just focusing on the left half of the coordinate axes now. If that happens, notice what the graph is doing. As I move in the positive x direction, my values decrease. They're getting smaller and smaller. And then once my derivative becomes positive, so now we're going to focus on the right half of the coordinate axis, now my derivative is positive, it's above the x-axis, and my function increases. Its values start to get large again. And so the observation is that if, and I'll put this as 2 points, if f prime of x is negative, then f of x is decreasing at x, and if f prime of x is positive, then f of x is increasing at x. And I haven't formally defined what increasing and decreasing mean, but I think that intuitively this notion should be fairly clear. If my graph is sort of going down, then I'm decreasing, and if I'm going up, then I'm increasing. Again, there's more we could say about the derivative graphically, but this is one of the first observations that I wanted to make sure to point out. And I suppose I should have labeled my pink line here. Okay, so that's everything for graphically. The last thing that I want to do is do a few particular derivatives in general. So for several functions, I want to compute their derivatives and then kind of talk about why this is what you would expect for the derivative. So derivatives of several functions. So the first example I want to do is, and maybe we'll put this in purple because it is an example. So example 1, f of x equals c for some number c. So f of x is a constant function. It does not change. It is exactly just constant all the way along. So if I were to draw a graph of this, not even going to label the axes a lot, but maybe c is right here, then the graph of f of x just looks like this. So f of x equals c. And so if the graph of f of x looks like this, and we know that the derivative represents the instantaneous rate of change of a function, so it has something to do with the rate of change of a function, and f of x is constant, that is, it's not changing, what do we expect the derivative to be? Well, since f of x is not changing, we expect f prime of x to be 0. That is, the rate of change of f of x is 0. It is not changing. It is constant. So let's actually do the limit computation and see this. So the limit as h goes to 0 of f of x plus h minus f of x over h. So there's my limit definition, and then if I put in what f of x is, well, f of x is c for any value of x. So this is the limit as h goes to 0 of c minus c over, I almost just said 0. Yeah, there we go. And c minus c is just 0. And since h is never equal to 0, this limit is 0. And so indeed, the rate of change, the instantaneous rate of change of f of x is 0, because for a constant function, you simply are not changing. Okay? The other example that I want to do is f of x is linear. So f of x is equal to mx plus b for some numbers m and b. That is the slope and the y-intercept here. So recall last time we said that instantaneous velocity, instantaneous velocity was the slope of the tangent line. And so in just the same way, the instantaneous rate of change, so just more generally, not velocity, but just any old rate of change, is the slope of the tangent line. And if I draw a graph, we'll put it over here, make some space. I'm kind of getting punished for using gel pens. And I draw just any old linear function. So this is f of x equals mx plus b, and then b would be like right here. Then, well, if I try to draw a tangent line at any point, what am I going to get? I'm going to get precisely f of x as the tangent line. So the tangent line to a line is the line itself. So since the tangent line of a line is the line itself, we expect, well, if the tangent line is just the line itself and the slope of the tangent line represents the instantaneous rate of change, that is the derivative, then we expect the derivative to just be the slope of this line. So we expect f prime of x is just m. Okay, well, we expect that. Let's go ahead and see that that's actually what we get. So the limit as h goes to 0 of f of x plus h minus f of x divided by h. Now let's go ahead and just put in our definition for f of x. So this is the limit as h goes to 0 of m times x plus h. So that all this function is doing is taking our input, multiplying it by m, and then adding b. And then minus, so this is f of x plus h, and then f of x is just mx plus b. If we do a little bit of simplification, well, m times x plus m times h, so we distribute the m to both of these terms, plus b, minus mx, and then the negative distributes to both of these, so this is minus mx minus b divided by h. Notice what happens, I have mx plus b minus mx minus b, so this just leaves us with the limit as h goes to 0 of m times h over h. The h's cancel, and bada boom, we have that this is m, as we expected. And so this is by no means all of the possible derivatives we could compute, but this should at least give you courage that the limit definition that we've given here is the sort of right definition. In mathematics, we often have a choice of how we want to define all of these things. We could have defined instantaneous rate of change using a host of other notions, but and in fact some people have. There are other ways to teach calculus rather than just limits. But the limit definition of a derivative really does represent a good definition. It does the things that you want it to do. It captures the pieces of information about functions that you really hope that it does, at least in these particular examples. And you know, since calculus is such a well-developed subject, you can sort of conclude that much more generally this does happen. Okay, so that's everything for this first introduction to derivatives. In the next couple of videos, we're going to expedite this process of computing limits. We're not going to do a limit every time we need to compute a derivative. That would be a lot of work. So in your homework, I'll have you do a few particular limit examples, doing sort of by hand these limit computations, and then we'll get into doing these things more quickly, because that's what we actually use in the real world. All right, see you guys in the next video.